Okay, on question number one, we have a voting scheme here where we have a quota of 10 votes needed to pass some resolution, and we have 5 voters, each with some amount of power. So to have veto power, basically without your vote, it's impossible to pass. So for example, if A withdraws vote or votes no, the total of the other 4 would be 7 votes, which couldn't be the quota. So A has veto power. And by that same principle, B and E also have veto power. There is not a dictator in this system. In order for there to be a dictator, you would need 2 things. You would have to have that person have veto power. So we do have 3 contenders here for a dictator, but they would also have to be able to pass a resolution on their own. So one of these 3 would have to have at least 10 votes just for him or herself, and that's not the case for any of our voters. And finally, the winning coalitions. I suggest writing these out systematically. So maybe say, how many winning coalitions are there with 5 voters, with 4 voters, with 3 voters? One thing you can use to help you is anyone who has veto power must be in every winning coalition. So you have to have A, B, and E in there. And that alone is only 9 votes. So then we have to figure out all the different ways to add to get above 10 votes. Okay, on 2 we have some voting methods here. First one being plurality. So we're looking at the highest number of first place votes. J has 3 plus 6 has 9 votes, which is more than B or N. For part B, plurality with elimination. So N was in last place there when we looked at the number of first place votes. So we go ahead and eliminate N and make it down to just J and B. And you should get something like this, which shows you that B would then have more than J in terms of first place votes. So B would win that. Board account, we have 3 different candidates here. So first place is going to get 3, second place gets 2, third place gets 1, and here's a mapping of how that would all work out. J would have the highest amount there. Pairwise comparison, there's 3 contenders here, so they're each going to go head to head, J versus B, B versus N, J versus N. And when you do that, you basically do it like part B where you ignored N. In fact, we already have, when we ignore N, J would get N votes, B would get 12, so that's right here. And then you ignore J, you ignore B to get these. Finally, B would get 1 point for each of the head-to-head wins, so B would get 2 points, J would get 1, N would get 0, and B would win with this method. Condorcet's criteria says that if you beat everyone else head-to-head, you should be the winner. So first of all, we have to look, did anyone beat everybody else head-to-head? We did find out that B beat J and B beat N. So according to Condorcet's criteria, we would want B to be the winner. And in the plurality with elimination, B indeed was the winner. Pairwise comparison, B was the winner. But in these other 2 methods, plurality and board account, B was not the winner. So these 2 would violate that Condorcet's criteria. Here we're limited to 5 digits if we're not allowed to repeat, and there's no other limitations on what we can do. We'd have 5 choices for our first digit. It could be 1, 3, 4, 5, or 6. Then whatever digit we've used, we can't use that here, so we only have 4 options, then 3 options, and finally 2 options for our final digit. That would give us a total of 120 numbers using these 5 digits with no repeats. Here we are allowed to use repeats, but we have to be between 3,000 and 6,000. Notice that all the numbers between here start with a 3, a 4, or a 5, except for the number 6,000. But 6,000 doesn't count because we're not allowed to use zeros anyway. And even if we were allowed to use zeros, we would probably want to count that one separately because we don't want to think of all the other numbers that could be formed starting with 6. So let's focus on the 3,000s, the 4,000s, and the 5,000s. Choose our first digit right here, 3 ways to do that. And then since we can repeat, we could use any of the 5 digits in the other 3 slots, giving us a total of 375. Here we have 2 CS majors, 3 education. If anyone can sit anywhere, very similar to this problem here actually. You basically have 5 different people who could sit in that leftmost seat. Then anyone except the person already sitting down could sit here. That's 4, 3, 2, 1, for a total of 120. If you do have to alternate, now since there's 3 education and 2 CS, there's really only one way for that to happen. You have to have education majors in slots 1, 3, and 5. If it were 6 people, 3 CS and 3 Ed, then you would have to first, step 1, choose whether an Ed comes here or a CS comes here, and that would take you 2 different options. But because we don't have to worry about that, because we know that this person has to be education already, we really just have 3 options there. Then 2 CS, 2 remaining education, and I just noticed a mistake here. This should really only be 1 CS major, correct? Because we already know that there's a CS major sitting here. So there's only 1 option here. So this would be a 1, and that would make 12. 3 times 2 times 2 times 1 times 1 would give us 12 here. So I'll change that on the PDF. And then if the 3 education majors must sit next to each other, we really have 3 scenarios here. Either they're the leftmost, the middle, or the right. So let's look at them separately. If they're the leftmost, we position then 3 choices from among the ed majors, then 2, then 1. Then we have 2 choices for which CS, either Chris or Claire, sits there, and then no choice here because it's the other one, whoever's not sitting here. So that gives us 12. We get another 12 by this plan, another 12 by this plan. None of these plans are the same, notice. They can't be the same because the 3 eds are in different places here. So we total that up for 36 different seating arrangements. Here in part A, we're looking at a permutation. So 18 to choose from, we're choosing 3, so P18, 3. This would give you the same 18 times 17 times 16 would give you that same number. Here, it doesn't matter what the order is. We're just choosing 2 out of the 18. So we have a combination, 18 possibilities. We're choosing 2. And then on the third one here, we have 1 education major we want to choose. So 13 options to choose from. We're choosing 1. And 1 out of the 5 non-education majors. Okay, drawing 2 cards, probability they're both aces. Well, in our first draw, we have 4 out of 52 of the cards are aces. And then after that first draw, we only have 51 cards remaining. 3 of them are aces. So if we want to get another ace, it's 3 out of 51. That's one way to get your answer. And this would be a fine answer there. 1 out of... This is actually the precise answer. This is a rounded estimate. So I personally like this one better, but either one is fine. Another way to think of it, all the different ways you could choose 2 aces. Well, there's 4 different ones to choose from. You're choosing 2 out of them. And then 52 different cards to choose from. You're choosing 2 out of those 52 cards. This would give you the same answer as this once you reduce it. Rolling a dice 2 times, probability to get at least 1 1. Whenever you see this at least 1 of something, it's usually easiest to get the opposite. So figure out the probability of getting no 1s and then subtract that from 1. So if we do that, probability of getting no 1s, well, in your first roll, you'd have 5-6 chance. You could get a 2, 3, 4, 5, or 6. And on your second roll, you'd have a 5-6 chance, 2, 3, 4, 5, or 6. Multiply those together to get 25, 36. And then subtract from 1 to get 11. You could actually get this directly also. Think of the total number of rolls that have at least 1 1, and there should be 11 of those. 36 total rolls, so 11 out of 36 by that method would also work. Either a 5 or a red, so when we're looking for the probability of a union, we want the probability of each separate one minus the probability of the intersection, minus the probability that both are there. So there'd be 4 5s in the deck. That's how we get 4 out of 52 for this. Half of the cards are red, so 26 out of 52. And there's 2 red 5s. You'd have the 5 of hearts, 5 of diamonds. So we'd subtract that out to get a total of 7/13. Here we have a conditional probability. So given this information that the sum is even, what's the probability we got at least an 11? So the formula tells us we have to take the intersection on top over the probability of getting that, whatever that information is. So being greater than or equal to 11 and even, well, if you're even, you can't be 11. So if you're going to hit both of these criteria, you have to have a 12. And there's really only one dice roll that will give you that 6, 6, the double sixes. So 1 out of 36 of satisfying both of those conditions. Probability of getting even, half of the results are even, so we put 1/2 there. Simplify it down to get 1/18. Here we have a chart. We want to know a few things. First, we want to know randomly selected student is non-Mennonite. So notice we have a breakdown here of 3 different groups of non-Mennonites, but we didn't really specify anything about where they're coming from. So more importantly is this 800 total out of our 1010 students are non-Mennonite, so we just divide those two. Here we have non-Mennonite attending rural, so here we do want to look at just this one category, so 250 out of the total 1010. And finally, given that the student attended a rural high school, so we're only looking at these 320 now. We're completely ignoring these because this is that additional information we have. So out of those 320, 250 were non-Mennonite, so we divide those two to get our answer. Incidentally, this part C is a conditional probability, so you could use that formula that we used right here, and that would also give you a correct answer.